Okay, so previously we've been talking a lot about the model theory, and I had sort of mentioned that we want to also look at the proof theory. And I mentioned that roughly the idea is that we want to make the most of the the domain equation that describes the types. So as an example, here's the domain equation that describes the types. For the row calculus, right? So you have the branch which is 0, the branch which is a for comprehension, the branch which is an output, the branch which is parallel composition, and the branch which is dereferencing a name, and then names are quoted processes. And then here is the collection that we want to use for our logical operations, and this is just cons list. So notice that if you, well, let's recall. So what we're ultimately going to be doing is taking, let's see, yeah, we're going to be taking an equation like this and turning it into the type specification, right? So what we have here is that the all of these things are going to be turned in collections. This is going to be turned into a collection, and that we have types for each of the unfolded branches, and then we have a kind, two kinds, which represent the two different sorts. So we have both types and kinds, in our type specification. So a statement like this is from nothing. So we don't have to have any assumptions, right? So there's no assumptions here, whereas there are clearly assumptions here, right? Because we have a non-terminal here. So from no assumptions, we can get that the instance 0 is of type 0, which is of kind P, right? So so this is sort of the witness for the unfolding, and this is the injection from 0 back into P. So the fact that this is really going to be modeled as a coproduct means I have an injective map from here back to here. All right, so that's how we interpret a statement like this. Similarly, with something like this, we're going to say that given that I have a witness for the type X, which is of kind N, and I have a witness for the type Y, which is of kind N. So I have a couple of names, and they may have specific structure that is articulated in the X and the Y respectively, and that I have a witness for the type U, which is of kind P. So I've got a particular process that may have some articulated structure. Then I can form the for comprehension, and it will be of type for X from Y, U, which is of kind P. So let me stop there and see if that makes sense. If the readings of these two type judgments, these are really introduction operators or productions, if that makes sense.
For me, it makes sense.
Okay.
Is it possible that with dependent types we can unify or we can like lift the small x to bigger x?
Oh, possibly. Yeah. I haven't looked at the dependent types part of this yet.
Mhm.
Haven't needed to. Yeah. Um, okay. So the rest of these things go through pretty much as we expect. Now Mike and I are still working on the collection part. But I'll just give you a flavor of what's going on and know that this is probably going to be revised. Um, uh, so um, we don't, if this really is empty, then we don't have a witness for empty, right? There isn't going to be, if we think about this colon as being membership, right? So this that lives inside that, and this injects into that. Um, well, if this is empty, well, there's an injection from empty into list. But what we don't have is a witness for that. So still sort of thinking about whether that's the right way to do it, or because we do have this, right? So there's an injection from this thing back into there. So we have to think a little bit about that. Um, likewise, if we know that A is of kind P and empty is of kind P, then list A is of kind P. And then we have a similar sort of thing here for the ends, right? So what these two pairs are doing is giving us lists of processes and lists of names, and the two are not connected, right? Except through the recursion of names and processes. And then here, we expand the same thing for inclusion of list, right? So this says that, yeah, I have to go back and fix these and get rid of these witnesses for a second. But anyway, this is saying that if I have a non-empty list, then that's a list. And this is saying that if I know that this is of type A, yeah, that the type A is of kind P, and list A is of kind P, then I can form the type, which is not an empty list. And then this needs to do exactly the same thing. So I'll get rid of the witness here for a second. That, and then the same is here. So we're still kind of futzing about a little bit with the collection calculations. Not as happy with that just yet, but we're getting there. But hopefully this makes sense. At least at this level of specificity, right? So we're building up two different notions of list that are lists of names and lists of processes, and we know that these things here are going to be lists, right? And this is the list of all names, right? And this is going to be a list of some kind, and this is the list of all processes. So the fact, so now when we think about membership, it's not like set membership. It's that this thing occurs somewhere in that list, right? And this thing occurs somewhere in that list. That's what the colon is saying, right? So so the whole point of generalizing the collection is that the colon is a generalized notion of membership. It's not just set, which would then give us the ability, if we carry out the generalization correctly, then we can also have this membership predicate not be just binary truth values, right? It can also be, elements of a quantile or probability distribution or something like that. So that's why taking good care of what's going on in the collection is very important, because we want this to give us probabilistic logics as well. Is that making sense?
Yes, yes.
Can you clarify what the double colon symbol is in the last three?
Oh, sure. That's const. So what we're saying is this A is const onto that list. So this A, which happens to be of kind P, is const onto that list. Does that make sense?
What does const mean? Sorry.
Oh, so yeah, sure. What we're saying is that this whole list here decomposes into a head and a tail, where the head is A and the tail is some list A.
Okay, yeah. Fine.
Sure. Any other questions or comments?
You said that when we say that X colon bigger X, it's not like a set type, set like.
Right.
But is it correct to say that it is a type, that X, small x is type of X? Does this cover?
So the bold things are types or kinds, and these are tokens or terms. So this term occurs in this type, and this type is going to be, I'm going to be able to find an injection from this into this.
I want to ask you about injection, but first I want to ask about types. So you're saying that types can be rich enough to cover all of the cases that you want, all the probability.
It'll be all the cases that are determined by your input, right? So your input is your model of your input is the model of computation, right? And what comes out is the type system, right?
Oh, I see. Yeah. And when you say injection, why are you, how to interpret it?
Just like you have a co-product, right? So it's a categorical co-product, right? So I've got some tagged union, and that tagged union injects into the co-product. So each one of these cases has a tag, right? And there's an injective map from there to there.
Oh, you're basically saying all of this constructor will create the P type or P kind.
That's right. Yeah.
I see.
So yeah, so that's kind of where we are. I think this is concrete, actionable. We know how to implement this. Just want to make sure that we get this collection stuff really nailed down. But I like in Rosette, we had the ability to detect that you had an empty queue or a non-empty queue. That was part of the type level apparatus of Rosette. So the fact that this is showing up, here, we can detect empty or non-empty. That's great, right? I mean, it's a level of specificity, because like if you were going to use this list to implement a pop and a push, right? So you're going to implement a stack on top of list. You'd like that a pop on an empty list is an error, right? A type level error that the compiler catches, as opposed to an error as opposed to a runtime error. So right? So with this kind of thing, we can do that, right? We can implement stacks on top of lists like this and catch at compile time pops on things that don't have at least have a head.
Like
Go ahead.
I'm thinking about the H list or
Yeah.
in Scala, the H list or this vector with a length on the type level.
Yeah, exactly. That's the kind of thing that we're automatically generating. That's correct. Yeah.
So
Yes, go
one
ahead.
more question is,
Mm.
you're by construction, you're disallowing like having processes and names in the same list.
Uh-huh, that's correct.
Okay.
But it's not, but this list is not like a value level list, right? What this list is talking about is the interior structure of these things. So the X's, the Y's, and the U's, they have an interior structure. And in standard type theory, those are typically sets of some kind or sets with structure. And what we're saying is that all of this stuff here, all of this list stuff is describing the interior structure of these things. So that's it's a little bit tricky to get it all right. To make sure that we understand all the pieces. Um, um, so
And list is really concrete, right? You want to be even more general than just a list, right? This is just example with a list, right?
that's correct. That's correct. And in fact,
Mhm.
in general, what we're gonna do is we're gonna punt a little bit. Yes. Here we go. So what we're it turns out that I don't think we've been able to satisfactorily compute like individual theory from a given model. So it seems like the thing we have to do is we have to have if someone is going to present a collection in a way that doesn't have certain properties, then we're going to have to insist that they give us a triple, where the triple is the theory side. So something like, true, negation, and conjunction. Right. So if they're going to present like this, as opposed to presenting like this, right? So, sorry, like this, right? So this is a model that has a certain kind of property, and this is a model that has a certain kind of property, right? And what we're saying is that if you don't have those properties, if you're going to present your theory of collections more like this, then we have to insist that you give us a triple. So there's your theory, and then there's a model that has those properties, and then there's an interpretation that links the theory to the model. And really what we're saying is that you've got some theory. You've got an equivalence relation. You've got a theory, so the free theory, some equations, a map from the free theory modulo the equations to the model and the model itself. Right. So that's really what we're giving. And what that allows us to do is to handle notions of negation. Right. So as we mentioned before, when the collection is a monoid like this, then right? So this is lists, right? So it's all, it's like it's the, you know, the empty list, or the list containing one element, or the list containing two elements, or the list containing three elements, blah blah blah, all the way up to infinity, right? So that's a it's like a Taylor series expansion way of thinking about a list model. And then I can have a notion of context, right, and term, right? So this gives me a notion of sub, which is why I use the letter S here, right? And so so sub can give me a notion of negation, right? I take the part out of the context. So if I can get the original thing by breaking it up into a context and a part, then I have a notion of negation, right? So this is, I can take the complement of this thing, which is that thing, right? Or it's really this thing minus that thing. And so this gives me enough structure to be able to model formulae like the prime formula that I mentioned before. So if you'll notice over here, there's our input, there's our output, and now notice that I can't write down the famous motivating formula that is so cool, which is this one. Prime is defined to be, it's not the identity, and it's not the decomposition of things that are not the identity. All right, so that picks out the generators or the prime elements of any monoid, right? Which, and since, you know, since we can see that this and this together make this thing a monoid, right? So it's clearly a monoid. Then we get that this formula, in addition to picking out the primes, also picks out the single-threaded processes. So there's a deep connection between primality and sequentiality, which is cool. That's awesome, right? Unexpected, but there it is. But this formula we can't get from this type system because there's no negation here. But we want to get that negation, so we can provide that negation using this kind of apparatus here, along with an interpretation like this. And so that does the trick. So we can recover this motivating example formula. So yeah,
that makes sense.
So that's kind of that's all I wanted to talk about today. Any other questions or comments? Well, we're at the point where we can start coding this stuff up. It'll be really fun to start eating specs for languages and generating the type systems for them, and then having people use the type systems to both prevent bad behavior or ensure good behavior, and also to start searching on repos for stuff that matches properties.
I was looking at Scala dependent types and what how to use it, and I somehow decided that with Idris it will be like much easier. So I would like to do some like a simple example in Idris.
Sure. Yeah. I've been thinking about picking up Idris, but Idris didn't seem ready for prime time in terms of production code. That's why
I mean, they have the version 2, which is
okay.
like improved version, but I'm still not sure that is completely like performant wise, like
Yeah, exactly. Notice that with the for comprehension for row calculus, we can start using so let's put this in context, right? So suppose I've got something like this. I should really flip these around, but whatever. Okay, so imagine that I add to the for comprehension. This is bugging me. I'm going to flip it around. I'll do the same here. Okay, all right, that's done. Okay, so imagine that just like in Scala, I add a where clause, right? So I do if, now I have some C that I apply to Y. Okay, so that's I've just added the where clause, right? Like with in the same way that Scala does. So now I can make C, I can give an interpretation for C, right? Where oops. So I could have C sub T. So I'll put a T here and I'll fix that in a minute. Y is equal to okay. So for some okay, and we're going to set this to be that Y inhabits T, just to be so this to be bold.
And by inhabits T, we're not just saying the structural side. This can be like a linear type where
Absolutely. Yeah. Yes. Right. And well, I haven't focused on the behavioral stuff, but the behavioral stuff fits into this perfectly. Right. But the point is that now Rolang becomes the query mechanism by which we can walk up. So if X is a GitHub source, right? I can walk up to GitHub, get a bunch of code, check that the code matches the type. So the type becomes a kind of query, right? So Rolang is like perfect for this kind of application, right? It's like it's almost as if it were designed with this application in mind.
Yeah, exactly.
So I think that'll be a lot of fun because then the blockchain starts to get really valuable, right? Because now we can the reason to stuff it into the blockchain is because it's a giant cache where you've already done these type calculations, right? You pull it out of GitHub and you only put into the blockchain that stuff which passes a type check. And so by the time it's in the chain, it's like you've memoized that particular type check. So you don't have to run it again, as an example.
Yeah, this totally makes sense.
So then our chain becomes super powerful, right? And there's a lot of reasons for people to come to our chain and to stuff their existing data into our chain, because our chain is performing these kinds of checks, right? So you do an import process from some GitHub repo or from some protein database or from some chemical database or cell signaling database, right? And this check might take a long time, right? Might take a huge amount of time. It's a big giant computation. But once it's done, it's in the chain, right? And the chain now just records the fact that what's sitting wherever we deposited this. So let's say that P as a result, what it does is at the channel satisfies T, right? It does an output of Y. So there, you see. So now we've memoized the check. So even though this computation was long, the next time you come to us and ask for all the things from that source that satisfied T, we'd return instantly as fast as it takes to go and get this off of the channel, satisfies T. So it becomes, if you think about it like a football field, or like a plane or something, right? The blockchain now becomes tipped so that the data pours into the blockchain, because there's all this huge value, because we've sifted through the data in a way that nobody else can sift through the data. All right, that's all I got.
So how do you describe this T? If it's some piece of code written in some language, then
That's what this is. These bold things are T's, right? So these small things, that's code, right? You can just read down the list here. This is Rolang, and so it doesn't have to be Rolang. I could put JavaScript in here, right? And then what will pop out for these X's and Y's and U's are types for JavaScript.
okay.
And so then these T's, so whatever languages you've got in GitHub, we can generate type systems for those languages, and then we can go and check the programs that are in GitHub for those types. And if they satisfy them, then we squirrel away that check. We memoize that check on the chain. And that also gives you a testament, right? It's like it gives you a certificate, like in a chain of custody or whatever. You can say, well, we got it from this source. We checked it for this property, and then we stored it on chain. So you've got all of that on chain. That whole process is now logged on chain.
Okay.
Which is important. Go ahead.
I'm thinking with running the program is the proof, right? And this check is, we are not really running the program, but we are proving something, right?
We're proving, yeah, it's like partial executions.
So it's something like what a compiler does, but it's more like it can describe many languages.
Yeah. So the algorithm goes from an input like this to a system like this. And the system can be thought of as a query language for programs that are defined like this.
Okay.
Cool.
Greg, can I show you what I wanted the last time? I checked the Zoom,
Sure.
and it's because it's something that I'm thinking how to maybe how to make it easier to index all of these types when we want to somehow bring this to what you are describing, and because this is like my naive thinking, which also like encodes types in some way, and so I have this GraphQL query example that I wanted to show my friends what I'm thinking, and because I built some systems in this way, where I encoded some code in the database, and I generated some type, and I did some compile time checking. So let me first just describe with how I'm using GraphQL. I'm using GraphQL just because it has this nice UI, which is doing some type checking. So, for example, here, let me first show, in GraphQL, we have this notion of a query and mutation. Query is just the reading, and mutation is updating or writing. And
Sure.
To working with GraphQL, we need to define the schema. And in my schema, I only have this items query with one item type. And this item type is like a basic constructor. This is the only thing that I have in the schema. So if I want to create some kind of user with some properties, which is like a different type, I cannot do this. This doesn't exist in the schema. And so in this my example, I call this GraphQL native. And I'm calling this native because everything is done with one schema. So this item type is the only one in the schema, but I can use this item type to expand the schema. So this is how I'm thinking, like a dynamical version of, or what you are describing with the linear types. This is something similar how I had in mind, so that I can issue some query to create new types and also to remove some types. But also I can influence what is the data on this type, because I have some like a query language to do that. It's very like a primitive, but you know, I was just using what I have in my hands, and this is why when I was listening to you the first time, I was amazed, because you were like answering my questions. You know, I had so much problems and questions, and you are the only one who was like explaining, oh, this is what we need to do, and I was, oh my God. This makes sense, right?
Sure, absolutely. No, I appreciate you sharing this. I mean, it turns out that it's like, these kinds of ideas, they show up in lots of people, right? It's just like the same with, with Newton and Leibniz, right? Both discovering calculus at roughly the same time. These sorts of, these ideas, they take hold of populations of people who are vibrating in the frequency of those ideas, and everybody is getting their particular view of the elephant. Yeah, that's cool. That's awesome.
And
go ahead.
I just want to show how this works.
Okay, yes, please.
This is a small example. So I have this basic mutations that I can do on the schema. So this is my database. This is the schema. This is the only the table that I have is this item table with self-reference. So and if I execute this items query, I don't have anything. So I need to use this item create, update, delete to update my schema. And so first I will create this root. I will explain what this means. And then I will create the user type. And this basically means I'm just updating this item table with some hierarchy. So what I did is basically this. I created the root item type, and this is like a root of the type hierarchy. And then I have something like an entity, which is like user. I have some number, string, or different basic types. This is like a ground types in Rolling. And this is how this looks like from the hierarchy perspective. And immediately now I need to refresh the UI, because GraphQL doesn't expect that mutation will change the schema. They know that the schema is static, but now I have the dynamical schema. So I need to refresh, and now I am able to see the types, because I expanded the schema. So now I have these users and I have this user type.
Yeah.
and I can so this is what I'm missing in the example, but I have exactly the same thing in production, where I created this self-referencing table, and now I can issue the new query to create the user type, which doesn't exist in the first place, and it doesn't exist statically somewhere in the schema. It's read from the database. Nice. And of course, I can go back. So, for example, now I don't have the node, for example, because the node doesn't exist on the user type. So I can go and I can add the node. I can issue another mutation and add the node to the user type. So now, if I refresh, now the node is here, in the user type.
Nice, nice.
And this is what is the next step. So when I have the root of the types, I create another root. This is what I don't have in this example. I have another root which is a root for the data, and it's linked with the types, so that I can validate. So this is what I'm giving the GraphQL, so that I have this validation. But I can also use this to validate the input, even without GraphQL. I'm just using GraphQL, but I can validate the data by the schema. And what I did on top of that, I added some code, and this is what I call this formula, because I was like mimicking the spreadsheet.
Sure.
So I was able to write some. The application was in C#, and I was using the C# compiler to give me all of the capabilities, because I didn't want to build my own compiler. So I saved this formula as a C# code into the database, so that when I want to validate the user input, which is completely dynamic, I can just use compiler to generate the whole code by the schema, and just use compiler to give me the result. So I see this very similar what you are describing as a C, yes. C of Y, right?
Yes. Yeah, exactly.
And of course, I was using the database because, from my perspective, I wanted to have everything indexed, so that I can write queries directly on the types. And I was using this CTA expressions, so that I can recursively, and this is how I'm looking when you say the last time when you talk about default. This is how I'm thinking about default, where I recursively go and look at the types, and I can compare the data and maybe execute some functions. For example, on SQL Server, they have like a special types for hierarchy.
Mm-hmm.
So
yeah, exactly. Yep, that's right. Yeah, I see the analogy. Yeah, it's exactly spot on.
Cool.
Yeah.
So maybe we can inject in the SQL in some kind of database and use indexing in the database without building this manually, to make it easier for processing as a intermediate step.
Oh yeah, absolutely. Yeah, totally. I mean, what we really need is compilers from the type system that we generate to the query language that is, some native query engine, like whether it's, GraphQL or Mongo or SQL, right? Right, and because those have been pounded on for decades, and so there are domain areas where they're going to be blazingly fast, and we're not going to write code that fast for decades. So much better to just write a compiler over to their system, and we'll still get speed, as long as our compiler isn't completely idiotic. Right? So yeah, so this is great. This is great. Very much in the same line of thinking. There is one area where I haven't really talked about it very much, but I'll just mention it briefly. One of the places where I'm trying to get to, you'll notice how closely the types mimic the programming language, right? And when you add in the modal formulae, allow you to contemplate an execution at the logical level that mimics the execution at the term level. So this is this is kind of like, lambda is to prologue, right? So we're getting a kind of prologue-y sort of thing over here. And so you can get an execution that mimics the logic, that mimics, logical computation, declarative computation. But so that's already interesting in its own right? So get a new class of prologue-like things. But where I'm really trying to get to is I want to be able to program the collective, right? So what's really here is a collective of entities, right? So they're programs, but they're entities of some kind. There's some kind of agency, and we want the collective to begin to behave in a certain way. All right, so think about it like I want to be able to throw a bunch of molecules in a beaker and know that that collective satisfies a particular formula, and because it satisfies a given formula, that collective is going to behave as if it were a one agent, right? So we want to be able to program at the collective level. Does that make sense?
Yes.
So that's part of what I'm trying to drive, because we're no longer at the point where we can satisfactorily program at the individual program level, right? In order to get to scale, right? If we're talking about an enterprise system that that's composed of billions of components, right? So think Internet of Things. Then we want all the components, that collection of components, to behave as if it were some gadget, and we want to be able to program at that level. And so I want to be able to provide the programming language, which is sort of the bold side of this, that allows me to program the collective as opposed to programming the individual. And that's true whether we're talking about the Internet of Things or whether we're talking about trillions of components, like the numbers of cells in an organism.
For me, it's difficult to imagine how would this looks like. How can I grasp this kind of?
But no, you're exactly right. It's very difficult to grasp. But that's why I'm trying to generate it automatically, right? So that programming the collective looks exactly like programming an individual.
Oh, I see.
Right. So it's like those pictures that those mosaic pictures, and like where you see this picture of Nelson Mandela made out of lots of little pictures of Nelson Mandela. Right. That's kind of what I'm trying to do, is to provide is to provide this ability to program the collective as if I were programming individuals. And I think that that's going to be super powerful, right? Because we've already surpassed this scope where programming individuals is even practical. We have to program at the collective level. It's where we are, both in terms of our own systems, but also in terms of the systems that we want to interact with, right? If we're going to build, genetic programming, if we're going to, or DNA computers, right, then we have to have the ability to program at that level. And I suspect that the same will be true when we have quantum computers at scale as well. But that's another discussion. All right, 5 minutes till developer stand up. I'm going to stop here. Thank you, everyone, for a very stimulating conversation, and I will see you next week. And many of you in just 5 minutes. All right, that's all.
Bye.